Scheduling algorithms, priority scheduling. At the end of this lesson, you will be able to describe priority scheduling, illustrate priority scheduling with examples, elucidate preemptive and non-preemptive priority scheduling, discuss the limitation of priority scheduling, indefinite blocking, elucidate the solution for indefinite blocking, aging. As you already know, the SJFS, that is, shortest job first scheduling algorithm, allocates the CPU to the next process with the smallest burst time or CPU execution time. That is, whenever the CPU is available, it is assigned to the process that requires the smallest execution time to complete. From this, you can observe that SJFS always prefers shortest jobs even when longer jobs are in the queue for a long time. So, the process which has the smaller CPU burst has the highest priority and vice versa. Hence, SJFS is a special priority scheduling algorithm where the priority is given based on the CPU burst time. However, the priority may also be assigned based on the user request, resource, memory, etc. This can be termed as general priority scheduling. Let us discuss general priority scheduling in detail. It gives relative importance to every process and assigns the priority precisely. Static priorities work well for real-time systems, while dynamic priorities work well for general workloads. Generally, priorities are defined using the fixed range of numbers like 0 to 7 or 0 to 4095. There is no particular rule for assigning either high or low priority to the value 0. In some systems, low numbers are used to represent higher priority, while in other systems, they are used to represent lower priority. In most cases, the lower numbers represent higher priority. We will also follow the same in our examples. Priorities can be defined either internally or externally. In internal priorities, some measurable quantity or quantities are used to compute the priority of a process. For example, priorities can be computed using time limits, memory requirements, number of open files, and ratio of average I/O burst to average CPU burst. External priorities are set by the factors other than OS, that is, outside the OS, such as the significance of the process, type, and amount of fund spent for the use, department sponsoring the work, and so on. Priority scheduling can be implemented either in a preemptive or non-preemptive manner. When a new process enters the ready queue, the priority of the new process is compared with the currently running process. If the priority of the newly arrived process is higher than the priority of the currently executing process, then preemptive priority scheduling algorithm will stop the execution of the current process and will start executing the new process. But in non-preemptive priority scheduling algorithm, it simply adds the new process to the ready queue. Let us discuss non-preemptive priority scheduling with an example. Consider 5 sets of processors P1, P2, P3, P4 and P5 with the CPU burst times 10, 1, 2, 1 and 5 milliseconds, which arrive to the ready queue at time 0 milliseconds with the priorities 3, 1, 4, 5 and 2 respectively. The processors from the ready queue can be scheduled using priority scheduling as shown in the Gantt chart. First, priority scheduling allocates the CPU to process P2 as it has the highest priority, that is 1. So, the waiting time and the turnaround time for the process P2 is 0 millisecond and 1 millisecond respectively. Next, the CPU is allocated to the process P5 as it has the second highest priority, that is 2. Hence, the waiting time and turnaround time for the process P5 is 1 and 6 milliseconds respectively. Similarly, the other processes are allocated to the CPU based on the priority, that is, it will be allocated in the order P1, P3 and P4. Thus, the average waiting time and average turnaround time for the given set of processes are 8.2 and 12 milliseconds respectively. In priority scheduling, a major problem is indefinite blocking or starvation. A process is considered as blocked if it keeps on waiting for the CPU in the ready queue. Indefinite blocking occurs when high priority processes are continuously added to the queue, that is, the CPU may get heavily loaded with high priority processes that the lower priority processes never get the CPU. The low priority processes get the CPU only when it is lightly loaded. In the other cases, the computer system may crash and lose all the unfinished low priority processes. The indefinite blocking of the low priority processes can be solved using the technique called aging. In aging, the priorities of the low priority processes are increased gradually based on the period of time they wait in the ready queue. For example, consider a priority range from 127 to 0 in a system in which 127 is the lower and 0 is the higher priority. Here, the priorities of the low priority processes are increased by 1 after every 15 minutes. That is, the lowest priority value 127 will become 126 after the first 15 minutes. Even a process with a lower initial priority, that is with value 127, would get executed with higher priority after some time. In fact, it takes a maximum of 32 hours to make the lowest priority process with value 127 as the highest priority with value 0. Summary. In this lesson, you have learned that in priority scheduling, each process has a priority and the process with the highest priority is allocated to the CPU. Generally, priorities are defined using the fixed range of numbers like 0 to 7 or 0 to 4095. In priority scheduling, a major problem is indefinite blocking or starvation.